Hello, good morning. I'm Bhavani from University of Texas at Dallas, and my talk today is going to be multi-generational database inference controllers. So this is a topic, that's the inference problem, that has been studied for the past 40 years. So I'll give an overview of the inference problem, and then I will discuss the different generation inference controllers. So I got into the field when I got into cybersecurity in the fall of 1985. And I was very actively working in this field for about 10, 15 years. And I'm still working in this particular field off and on for the last 20 years. So the first generation of database inference controllers, I would say from 1980 to 2000. And then the second generation, I would say from about 2000 to around this time, 2020. And the third generation, that's sort of the future. Where do we go from here? 2020 to 2040. And then I will provide a summary and some directions. So what is the inference problem? Inference is forming conclusions from premises. And the process will become a problem if the users draw unauthorized information from the legitimate responses that they receive. So, you can post query A, get some response. Query B, get some response. You put the two responses together and infer something that is highly classified, okay? So the inference problem arises in databases, and that has been studied, as I said, for close to 40 years. It started with statistical databases, especially Census Bureau. They were studying statistical databases to study populations and so on. And then later, there were inference controllers that were being developed, especially by my team at the MITRE Corporation, using deductive database techniques. And there's also work on privacy problem. In a way, you can view privacy as a form of inference. For example, inference, you can put collections of data together and infer something that is highly classified. For privacy, you can put collections of, say, public information together and infer something that is highly private. That's sort of one aspect of privacy. So database inference controllers, they're the systems that prevent a user from drawing these unauthorized conclusions. And in this presentation, we have divided these database inference controllers into 3 generations. The first generation, and as I was actively involved in that work. The second generation, which is sort of ending, I would say, and I've been involved in that work as well, off and on. And then what's there for the third generation? And if history has anything to go by, I would say the third generation would be from about 2020 to around 2040. So, first generation, what did we do? The first generation of inference controllers, they were developed around the early 1980s with statistical databases, and then moved on to multi-level secure database systems, and I'll explain in a minute. With statistical databases, organizations such as the Census Bureau and also epidemiologists were interested in studying different populations, while at the same time ensuring the privacy of individuals. So they use techniques such as perturbation and randomization to ensure data privacy. So much of the work on database inference controllers, as we know it, started with the Air Force Summer Study in 1982, and their focus was designing and developing multi-level secure database systems. And in these systems, users are assigned different clearance levels, and the data is assigned different sensitivity levels, and users access the data according to the sensitivity level of the data and the clearance level of the user. However, it is possible for users to pose, as I said, legitimate queries and assemble the responses and subsequently deduce highly classified information. This problem is known as the inference problem. Therefore, many of the first generation database inference controllers augment database systems with inference engines and analyze data and the responses to the queries and determine whether the responses should be released or not. So we have done, as I said, a lot of work since around 1985. My first paper actually was published in 1987, but I was actively involved from about 1990. And so I proved that the inference problem was unsolvable, and then we looked at the solvable classes and tried to provide solutions. There were a variety of solutions. On the one hand, we examined conceptual structures such as semantic networks to represent and reason about the applications. And then much of our work focused on augmenting, say, commercial database systems, multi-level systems such as Sybase. It was a fairly large database corporation, Sybase Inc., and augmented it with what is known as inference engine. And so we developed a system. We also patented the system, and it was designed and developed entirely in C programming language, and the policies were also in C data structures. Remember, this was around 1990. User poses a query, the policies, security policies are examined, we rewrite the query according to the policies. And before we give the responses, we look at, okay, what are the previous responses? Because remember, we don't want the user to put all the responses together and infer something that is highly classified. So we look at the release database, look at whether some responses have been previously released and whether the user can deduce something that is highly classified. So the challenge we were faced with, and several people asked me the question, how long do you keep this history database? Today we have mega databases, right? We can have data management systems that's managing petabyte and even probably zettabyte of databases, right? So we have systems like Facebook using data management systems, managing the data for billions of users. But remember, we are talking about 1990. Okay, that was, I think, 30 years ago. So of course, that was the legitimate question. So we would say that we are assuming there is sort of unlimited storage. But of course, you can only keep a certain amount of data. So we look at history kept for a certain period of time. Okay, so in addition, the inference engine will also use the logical rules to determine if we release a response R, can the user deduce something, say R star, which is highly classified, right? So for example, we said the ship's locations would imply the missions, but the missions are highly classified. So do you give out the locations? Similarly, from the medical records, you can deduce the disease. So do you release the medical records? That's from a privacy perspective. So this was sort of very high level overview. I've also listed some of our papers. So you have the inference engine, inference controller. It's managing the knowledge base. What's the knowledge base? All of the security policies, the history database, and then queries are posed through the user interface. And the inference engine also has attached to it some kind of query processor, will reason about the queries and the responses and pose the query to the multi-level database system. It will go to the multi-level database, get the responses, and then inference engine will look at the history. Should I release this to the user? Okay, so this took us actually quite a long time to design. It started in 1990, and I would say it took us about, well, over 1.5 years to design this complete system. Okay, so that's the first generation. And these were centralized inference controllers. So we have a centralized database, centralized inference controller. And this work we carried out for the Department of Navy. Okay, so later, the Department of the Army, they talked to us and they said they really liked what we are doing and they have a real need. So this was around 91, 92. They have a real need for this kind of work, okay, for a distributed environment. There was a particular army system which was distributed. Can we develop something like that for a distributed environment? So we designed and developed a system we call distributed inference controllers. I still call it first generation. So you have multi-level database management systems across multiple sites. So we say A, B, and C. And then each location has got a local controller that will manage the local database. So essentially what we have here is a local controller, right? So we also have a global controller because really local controller doesn't know what is happening at the other side. It will only manage the inference problem at the local site. Then at the global site, the global inference controllers have to communicate with their counterparts and decide whether information has to be released. So before releasing the information, the local controller will do the local work. The global controller will have to talk to his counterparts, which they will in turn communicate with their own local controllers and decide what information has to be released. Okay, so we published this paper actually in IEEE Transactions on Knowledge and Data Engineering, a top data journal. Okay, so now the second generation. So we are now talking about the year 2000. And that's about the time I went to the National Science Foundation from MITRE Corporation in 2001, actually, as an IPA to manage various programs in cybersecurity as well as information management. So as new technologies such as semantic web and reasoners emerged, database inference control work took on a new dimension. So instead of making deductions on data that was based on relational model, remember, our first generation inference controllers were based on relational data models. So data was stored in semantic web databases. And instead of SQL queries, now queries were posted in Sparkle. And Jenna is a RDF, semantic web database. And we also developed our own Sparkle query optimizer. At that time, we're talking about around 2008, 2009, 2010. There weren't query optimizers for semantic web databases. What about reasoning, right? Remember, we built this complete inference engine back in the early 90s. So for reasoning, we were using reasoners such as Pellet. Pellet was developed, I believe, open source, University of Maryland. And so we put together, remember, in 1990, we had to build everything from scratch. So here we are in 2005, 2010, we were able to plug and play systems, and our policies were specified in a language called SWIRL, Semantic Web Rules Language, queries in Sparkle, data in RDF, and then we had actually, database inference controllers based on semantic web, and then we also re-implemented them in the cloud for better performance. Okay, so some of these architectures were also extended to securing social media. So to the latter part of 2010s, that's the last 3-4 years, we've been focusing on big data technology and machine learning, and I think that's where the future is going to be. So again, looking at the second generation, so here we have semantic web-based inference controllers. We had Jenna, RDF Manager. It's open source, developed by, I believe it was Hewlett-Packard Laboratories at Bristol in the UK, and Pellet, University of Maryland. So knowledge base will be policies in SWIRL, and the history database we represented in OWL, web ontology language. Of course, our data is now RDF graphs, and the user interface, instead of SQL queries, we had Sparkle queries. And this took us only about 6 months to put together, or maybe even less. Why? Because all of these systems were there. All we had to do is to plug and play and tailor it for our problem. Okay, so we also developed, re-implemented, I wouldn't say implemented, I would say re-implemented, because we had to take advantage of the cloud, right? So our cloud at that time was Hadoop MapReduce infrastructure, and we had Sparkle Query Optimizer, right? So Jenna didn't really scale for us. So we had to build our own sort of Jenna, and we call it the Sparkle Query Optimizer, which was managing the RDF graphs, cloud-based policy manager, so we can really use Spell-It because we had to scale. So we built our own policy manager for knowledge-based policies in Swirl and the history also in OWL. And the user interface was Sparkle queries. And so again, we say cloud, but we use essentially the Hadoop MapReduce infrastructure. So today we would use Spark and various other technologies. So we published a book, right? It was called Secure Data Provenance and Inference Control with Semantic Web, and also a number of papers. So that is second generation. And I would say it's finishing about now, okay? So now where do we go? Third generation, which is sort of starting about now. And how would I proceed with this kind of work? Of course, we want to also look at some of the theoretical foundations. So for example, back in the 90s, I proved inference problem was unsolvable. And then I also developed a special logic for secure database systems to reason. What about the complexity classes? There's a lot of foundational work that needs to be done, okay? Which I'm hoping that I can, restart doing that work over the next few years. But the third generation inference controllers, of course, we've got to take advantage of all what's going on, data science and artificial intelligence. We now have big data management, which we didn't have in the 1990s. We were struggling at the time to manage even terabytes of data, okay? That includes systems such as MongoDB, Google's BigQuery, Apache Hive. Hive, I believe, was first developed by Facebook. Now it's open source. The big data solutions are being developed by cloud providers, including Amazon, IBM, Google, Microsoft. In addition, infrastructures platforms based on products such as Apache's Hadoop Spark and Storm are being developed. So there are infrastructure management tools as well as big data management tools. So a brief overview. Infrastructure management tools could be, as I said, Hadoop, it's open source distributed framework. It comes with MapReduce, programming model. Storage system is the Hadoop distributed file system, hosted on clusters of machines. MapReduce, as I said, programming model and an associated implementation that takes a client request and transforms them into MapReduce jobs. And these jobs are executed by Hadoop. The main feature of the programming model is the generation of the jobs. Apache Spark is an open source distributed computing framework, also processing massive amounts of data, okay? So third generation systems, the various components, application programmers use Spark through interface that consists of data structure called resilient distributed database. Spark was developed to overcome the limitations of the MapReduce programming model. Apache Storm is an open source distributed real-time computation system for processing massive amounts of data. So we have a number of technologies. Storm is essentially a real-time framework for processing streaming data and real-time analytics. It can be integrated with HDFS, that is Hadoop distributed file systems. And the data management tools are Hive. Hive is an open source SQL-like database data warehouse implemented on top of Hadoop MapReduce, initially developed by Facebook to store the information related to Facebook data. However, later it became an open source project. Trademark is essentially a data warehouse. It manages petabyte scale data. It runs on Google infrastructure and can process SQL queries or carry out analytics extremely fast. Of course, we have got the NoSQL database. It's a generic form for essentially a non-relational database design for scalability for the web. It is known as non-relational high performance database. The data models for NoSQL databases, they may include graphs, document structures, key value pairs, also column-oriented databases. Some of the NoSQL databases are such as MongoDB and HBase. Okay, so how does it look like? In the architecture for third generation inference controllers, I would say we are using big data management tools hosted on these infrastructures. So big data management tools are augmented with inference engines. These inference engines essentially implement various machine learning algorithms. So from sort of deductive and reasoning techniques, we are really now want to get into the full-fledged machine learning, including deep learning, as well as clustering. These algorithms will examine the policies, learn about the data, extract patterns. It could also look at what do the users know, what about their prior knowledge. because unlike 1990, where everything was coded in C programming language, even the data structures and the policies and the history, but now we have all of these AI techniques and programming in Python, right? So if I were to develop it now, I will do the whole thing right now in programming languages such as Python. Our second generation, we implemented the whole thing in Java. So third generation would be more Python. The algorithms will examine the patterns, learn about the data, extract patterns, and make predictions. And so these predictions could be highly classified predictions. If the patterns and predictions are not what the users are authorized to see, then they are not given to the users. We are now in the process of designing and developing such big database inference controllers. So it's a very rough architecture, and we still have a lot to do. NoSQL database queries, policy manager, inference engine, knowledge base. I'm saying Swirl and OWL, but it could be, we are looking at different knowledge representation schemes for big data. RDF is only one aspect. There are different types of knowledge representation now. So big data managers could be HBase, Cassandra, and the high performance infrastructure, Spark, Storm, and so on. Okay, so this hasn't really started. We are just doing some preliminary work. Now, where do we go? First, a summary. We have talked about various aspects of database inference control, right, across multiple generations, development of first generation controllers in the 1990s, and I would say lasted until 2000. This time there was a lot of work on statistical databases by Census Bureau and epidemiologists, and the goal was to protect the privacy of the individuals while deriving various statistics. Then came the Air Force Summer Study in 1982. The focus was on multi-level database systems, and I got started in this area in the mid-1990s, and I'm still continuing with such work. In our approach, in the first generation, we augmented Sybase relational database systems with inference engines, development in C. And we also developed distributed inference controller. So that work was carried at the MITRE Corporation. Second generation, I developed with my team at UT Dallas. And this was inference controllers based on semantic web. And we developed, Pellet, we used Pellet and Jenna, and then we also implemented these inference controllers in the cloud with our own policy engine, as well as our own Sparkle query optimizers. And during this time, there was also a lot of focus on data privacy, privacy-enhanced data mining, database privacy controllers. At the same time, we utilized some of the latest technologies, semantic web, and developed the second generation. And with the emergence of cloud, we implemented our inference controllers in the cloud. Now comes the third generation. Finally, the development, I would say, third generation between now and 2040, next 20 years. I have absolutely no idea how they will look in 2040, but now at least for the next 5 years, it's going to be big data and machine learning, data science, right? This third generation will take full advantage of all of the latest technologies. In our design, we are hosting big data management technologies on high performance infrastructures and developing inference engines that utilize machine learning, deep learning, and so on techniques. While much progress has been made over these 40 years, and we expect more progress over the 20 years, I hope I can be around for the next 20 years to work on these very exciting problems. We also need realistic examples and policies, right? Much of our work has been toy policies, such as if ships' locations are, ships' missions are classified, then the locations have to be classified if locations imply missions, or I will share my data with you, provided you don't share the data with John Smith. So these are sort of fairly toy policies. So we are really working with policy experts, especially cybersecurity policy experts, to develop realistic policies. Also, as new kinds of systems emerge, social media systems, they would be subject to inference attacks as well. Another point to note is that inference controllers themselves, this is very important because the secure database systems, the inference controllers that are supposed to be providing security features, they could be attacked, such as machine learning models we are using for the third generation inference controllers, they could be attacked. Therefore, we are also examining adversarial machine learning techniques to handle such attacks. So we've been doing some work for the Department of Army Research Office. My colleague actually, he's leading these efforts. And so I make some small contributions to his work. So that whole area is called adversarial machine learning. He's Dr. Murad Kantajulu. And so we can use some of these techniques, adversarial machine learning, perhaps to secure the machine learning models for the inference attacks. Now, this is an area I'm really a beginner now. I'm studying quantum computing. So what can we expect? Everybody's now talking about quantum, right? So how can we use quantum computing to manage the massive databases that store the history information? Furthermore, such novel computing methods could be used to enhance the processing of the deep learning techniques, right? How can you apply this machine learning on quantum computers? That's the big challenge. We need, and that's already been done in the beginning stages. So we need to examine such aspects in the design and development of next generation of database inference controllers that are high performing and secure. What is our goal in the end? That users cannot infer unauthorized information from the legitimate responses that they obtain, regardless of whether it be for data security, okay, security, or whether it's for privacy. So it's whether it's for inference problem or privacy problem. So I'll be happy to answer questions. You can please email me, bhavani.thuraisingam@utdallas.edu. I'd also like to acknowledge all the colleagues I've worked with over the last 35 years, almost this fall. And my colleagues at MITRE, colleagues at NSF, who have helped me to fund programs, and my colleagues at UT Dallas, especially my colleagues, Professor Latifa Khan, Professor Murad Kantajulu, and our project coordinator, Ms. Rhonda Walls. Thank you very much.